All right, so those folks should find their way back. There they come. Okay, so let's go back to here. All right, so that's the theory of public key cryptography, and now there's the practicality of actually implementing it, which turns out to be pretty painful. So Alice and Bob want to talk to each other. But the main thing public key cryptography solves is the key distribution problem. Now, Bob just has to publish his public key, keep his private key secret. Alice can encrypt stuff with Bob's public key and send it over there. Nobody can read it except Bob, who has his private key. That's the point. So you don't have to distribute any secrets. You never tell anybody the secret, and the thing you distribute is public for the whole world. So that solves the key distribution problem, at least a lot of it. All right, so now there are ways to use this. You can use it to do Diffie-Hellman key exchange, which was the heart of it all, where you send these numbers over the network that can be used to effectively agree on a key without sending anything over the network that's easily reduced to a key. That was the essential ingredient that made this all possible. Now you have non-repudiation because you have a signature algorithm, and the signature algorithm involves encrypting something with your private key, which anybody can decrypt with your public key, so everybody can verify that you signed it, but nobody can fake it because they don't have your private key. And that's digital signatures. And of course you have encryption. As we described, you encrypt with the other guy's public key, and you can move forward, and the big systems are out there: RSA, ECC, and LGML. RSA is the most popular. ECC became very popular recently because the NSA pushed it hard and it's much cheaper, and now people are sort of lost. Now the NSA has withdrawn the recommendation of ECC and told us all we should use something that doesn't exist yet to be quantum proof. People are just sort of stunned and not quite sure what to do right now.
So what's
yeah.
being used for mobile devices?
ECC. Mobile devices mostly use ECC because it saves battery life, right, and it's faster. Not by the NSA. The NSA says, they don't say it's broken right now. They say it will be broken when quantum computers come out. So they recommend that we phase it out and no longer deploy it, go back to RSA and make the key much longer, like 4096, and expect to throw that away in a few years when they come up with a quantum-proof algorithm. Because all these are going to be trashed by quantum computers. So that's the thing about cryptography. You think math is nice and stable, but it's not at all. Every year there's a revolution. Everyone's scared. All the stuff you trust is shot, like WPA2. You run around like chickens with their head cut off. It's amazingly exciting for something like math, which you would think would be like clear. There's one answer and the job is done. It's not like that at all. It's like you build a boat with a hole in it, and as soon as you patch one hole, there's another leak springs up somewhere, and you're just running around constantly patching it. So the problem with public key cryptography is it is extremely computationally expensive, much worse than I thought. And I tested this. So remember, we can do all this stuff in Python very easily, which is why I think it's perfect for this class, because the programming is easy, and you can play with these things and see how they work. So to use AES, you bring in AES in your Python. You need a 16-byte key, and you need a 16-byte plain text. Otherwise, you'd have to pad it with something. And I don't care about that right now. I just want to choose something that's simple. So I took 60 bytes for key, 60 bytes for plain text. I created a new cipher object, and then I do cipher encrypt plain text. That's going to use rotten old electronic code book mode encryption, but I don't care about that either. I just want to see how long it takes. So I encode it with hex, and you get this long hexadecimal junk, and that's the encrypted plain text. So I can just do the same thing with RSA. You encrypt RSA, you import RSA from crypto public key. Use a program that will generate a key pair here called key. Then you have a public key you can get there, key.public key. Then you can have a plain text, which is 16 bytes long. And you have ciphertext, which will just encrypt it. I don't know if I ever knew what that 0 is, but you got to have it there. Then you have ciphertext encode, and it's this long, horrible stuff, because RSA encrypted stuff has to be as long as the key, 2048 bits. So it's much longer and much more complicated. And if you want to decrypt, it's just key decrypt, and it decrypts back to the same old stuff. So you can encrypt and decrypt. So now you can write a little program that does this and measures how long it takes. All you have to do is import time, and then set something start, time.time, do whatever, and then print time.time minus start. So I just adjusted these numbers to be reasonable. So I did 1,000,000 AES, encryptions and decryption. And then I did one key generation, 4,000 encryptions, and 50 decryptions. I just chose these numbers because all those times come out about the same. So you can do 1 million AES encryptions or decryptions in half a second, or you can make one RSA key in the time it took you to do 1 million AES encryptions, or you can do 4,000 encryptions or 50 decryptions in the time it took you to do 1 million AES. That is really, really slow, more than 1,000 times slower. One thing that we're going to talk about next class in more detail, notice how encryption is faster than decryption. That's because you choose special values to make one faster than the other, just like your internet service provider gives you fast down and slow up. You can make it either way. Yeah?
When you're testing speed, does it matter for the amount of data inside the encrypted message?
And the question is whether the size of the encrypted message affects the speed, and of course it does. In this case, I made it always the same, 16 bytes, one block. So that seemed like a fair comparison, but perhaps you'd like to say that 2048 bits would be more fair because RSA is going to blow it up to that size anyway. Yeah, you could argue about that, but even if you did that, the end result is AES is much, much faster. But I think, sure, I'm sure all those things matter. I just did the simplest case to get a general clue of how fast they are here. And this is why you really have to do something more than just use public key encryption, or everything would be numbingly slow, thousands of times slower than it would be. So that's why we really use hybrid systems. You use public key encryption just to exchange a private key, and then you use private key encryption from that point on, just to make it faster. You could, and the PGP email encryption really does encrypt the whole thing with public key and decrypt the whole thing with public key. And you could do that, but it would totally cost 1,000 times as much battery life and CPU if you did that for normal internet exchanges, so they don't. They use this hybrid method where you use public key encryption just to distribute an AES key, and then you use AES. It just gets, the end result is just as safe and much cheaper. All right, so that's the game. First, Bob sends out a public key, then Alice chooses a random symmetric key and sends it back with Bob's public key. So now Bob has it and Alice has it. Now you can send back and forth with symmetric encryption. So the only actual thing you did with the public key was overcome the key distribution problem for symmetric key encryption. And that's what we're really doing now. But it relies, of course, this relies on both your public key and your private key algorithms being good. If either one of them is bad, you're hosed. So you could say you're increasing your attack surface. All right, and of course, one of the issues that public key encryption cannot touch is key authenticity. If you somehow send a fake public key to the sender and fool them with basically social engineering, then they use the wrong key to encrypt it, and now your encryption is shot. And this is essentially what SSL strip does. This is what Burp does by sitting in the middle. It sends you a fake certificate, your browser falls for it, if you configured it to fall for it, or if your app doesn't bother to verify the certificate. That's the problem. It's essentially social engineering. It's outside the domain of mathematics, really, but it is a weakness that can be exploited. So the current solution is digital certificates that are verified by trusted certificate authorities, and that's how we protect ourselves on the internet. And as we know, it's pretty good. Most of the time, it really protects you, but there are a few ways to defeat it, and nothing is ever perfect. So here's the main algorithms. Integer factorization schemes are RSA, and there may be some related ones, but RSA is by far the most popular, where the hard problem is factoring the product of two primes back into those primes. As long as that problem remains unsolvable, this system will work. Discrete logarithms use the discrete logarithm problem, which is just a generalization of the same thing, where you find what power you have to raise a number to make a specified other number. And that's also something that's very difficult to do backwards. And elliptic curves is yet another one out there, which works with much smaller keys at an equal amount of security, and was pushed very hard by the NSA until about a year ago. And here's the statement about how secure they are. 64 bits of symmetric key is what was considered secure until maybe 10 or 15 years ago, and not considered secure anymore. And that's like 128 bits of ECC or 700 bits of RSA. That's about what's currently been cracked. 80 bits is secure enough for everything right now. Nobody could even crack a 72-bit key by brute force. 80 bits is beyond that. So this is presumably completely secure from attacks right now. And 160 bits for ECC or 1024 for RSA, nobody's cracked any of these. But to have future proofing, you typically like to move up to 128, 256, or 3072. Then you might have some reasonable expectation that nobody will develop a crack in the next few decades to get in. Yeah.
What's the DL?
I forget. Sorry, I can't remember. Discrete logarithm. Discrete logarithm is the same issue, same length as RSA. So RSA or discrete logarithm, which we'll talk Elgamal then. Good. All right. So the problem is quantum computers ruin everything. Even making the key longer is essentially useless because the difficulty no longer grows with a strong function of the key, but a weak function. So your book guesses 2 to 3 decades away for quantum encryption. Because of the NSA's warning and the fact, there's another chip came out yesterday from Intel with qubits on it. It seems like the writing is on the wall that these things are really coming. All the necessary components have been developed. It's pretty obvious that the NSA already has one in secret. And within a couple decades, we'll have them. So this whole family of cryptography is going to go away, to be replaced by God knows what. But the NSA, the National Institute of Standards, has begun a contest, like they do every few years. And the contest here is to develop quantum-resistant encryption methods. So the mathematicians of the world are at work on it. And there will be a competition with rounds. And in 5 years or so, they will stamp something, the new replacement quantum encryption algorithm. I hope. And we will find out what you have to do to make something that quantum computers can't solve. So that's the game. Here's the NIST's recommendation from 2016. Here's where this all came from. So symmetric key algorithms like AES 128, 192, and 256 are here. And here's comparable strengths. So less than 80 is not secure enough. That's the orange. And so everything should be up in the green is what they recommend. And for top secret, they want AES 256 or comparable key lengths. And notice that RSA of 7,600 bits or 15,000 bits is not considered out of the realm of probability. So you might wonder how slow it gets. And I think I tried that. Yeah, I tried some of these long keys, and man, it's pretty miserable. The slowest operation of all is key generation. To generate a key, 1024 took 1/6 of a second. It took a whole second for 2048, and it takes 170 seconds to generate one key pair for 15,000. That's 3 minutes. This is getting seriously unpleasant. So, even without quantum computers, to make it secure enough, have some reasonable buffer begins to become really expensive. And you can see why they use ECC on cell phones and why all this stuff is pretty shaky and headed for the chopping block. We need something better. And the mathematicians of the world are currently scurrying around trying to invent something better. But it'll be a couple of years before they invent something and it gets tested and approved. Anyway, that's the game of that. I got some more cahoots. And then I want to talk, by the way, about cryptocurrencies. I'm going to talk about the projects, because now most of the projects are now going to be cryptocurrencies for a while, and I should demonstrate some of them. So this is 141.6b. All right. All right, 505.756. There they come.
And did you cover today news about the RSA library weakness?
Yeah, we talked about that. The RSA, the weakness of certain, which is not specified in detail, but certain RSA keys are apparently predictable. Yeah, and
they're gonna do a supplement on the 2nd of November.
Yeah, that's right. Yeah, so next month we'll know what it is. Like I say, they say it's not the random number generator. My guess is they chose a short prime number, which would be a way to make it faster, but not safe. Right, and that's the big issue, TPM chips. And apparently that means Windows BitLocker is vulnerable in old machines. So that's pretty gruesome. That's the problem with this stuff. You're trusting a bunch of people, and there's so many ways to do crypto wrong. And as you can see, public key cryptography really gives you a temptation to do something to make it faster. But choosing a short prime number is a very unwise way to make it faster. So I'm guessing that's what they did, but who knows? All right, wait another 5 seconds. All right, so 5 questions. Okay, which are these exchanges keys? Okay, that's Diffie-Hellman key exchange. Not a popular answer, but that's what it is. It exchanges keys. It's not a full cryptography suite. It's just a key exchange mechanism. All right, which one of these is the slowest activity? Decrypting is by far the slowest. You choose it to make encryption fast and decryption slow to make it easier for the client and let the heavy load be on the server where you expect it to be. Anyway, all right, which is the fastest task? All right, everything with AES is blazingly fast. Everything with public key is ridiculously slow. It's simple. All right. All right, what's the worst weakness in RSA? Okay, I'm so bothered with that answer. The rest, it doesn't use much RAM, and protecting your private key is no different than any other encryption. Generating public keys is slow, but it's not a weakness. The only problem is the CIA has to be trusted, and they can get hacked or betray you and your host. The whole system falls apart because then you don't get the right public key, and that blows the whole system.
You say trusting C8 and the CIA?
No, that's not CIA. It's certificate authorities. And the 100 certificate authority companies are the ones you have to trust. They hand out the public keys. And if they were to hand out the wrong public key or run some kind of insecure system that makes it possible to trick someone, which happens pretty often, then you're hosed. Then all the beautiful math does you no good because you're working with the wrong key. All right. So how long does an RSA key have to be as secure as AES 128? All right, apparently it's 3072 according to the NSA. I know 2048 is now the minimum recommended. 3072 apparently is even better. That's what we should all be using. Most people are still using 1024. Anyway, so W, Joker, and password. So I think we should take a break. I want to talk about cryptography, about the cryptocurrency. But let's take a 10-minute break and pick it up 5 minutes to 7. If you're W Joker, let me know who you are. Anybody in the room? Oh, good. Board Fry. Good. You're W, I guess. Yeah. Okay, good. So Joker's probably online. Why don't you send me a text and tell me who you are? I'll wait a few seconds for that. Then I'm going to stop the share and start it again in 10 minutes after break. Joker may be impervious to points. Apparently so. All right.